My name is Karthish Manthiram, and I'll be sharing with you today work that our group is doing on the electrification and decarbonization of chemical manufacturing. I like to start by putting up this image and just considering where the carbon footprint is. One might instinctively point to the gasoline-powered vehicles or to the electricity powering the lights, but there is in fact a carbon footprint behind virtually everything that we see in this image. There's a carbon footprint behind the plastic of the billboards, behind the steel of the flagpoles, the cement of the buildings, the clothing that everyone's wearing, and even the patty of the McDonald's burger. These carbon footprints are inescapable. We can look at this quantitatively. This plot shows the carbon footprint of the top 18 commodity chemicals as a function of their production volume. You'll see here that one chemical, ammonia, stands out above all the rest, and it has such a large carbon footprint that it in fact has its own y-axis. So if we're serious about decarbonizing chemical manufacturing, we have to do something about ammonia. And if we're serious about achieving deep decarbonization, that is near complete decarbonization of the chemical industry, then we will certainly have to find routes to decarbonize a wide range of other chemicals, each of which create a carbon footprint through very different ways. We can look at how we make ammonia today, and this will give us some insights into where we need to make progress. We often start this process beginning with methane and water, conducting the steam methane reforming reaction at greater than 700 degrees centigrade, along with the water gas shift reaction in order to produce hydrogen. So this is a reaction in which we're taking hydrogens off of methane and off of water and moving this oxygen atom from water onto this carbon from methane. That in turn means that we generate a stoichiometric CO2 footprint. That hydrogen then is reacted with dinitrogen to produce ammonia. And this is done at 400 to 500 degrees C and 150 to 250 bar. So there are two major problems here. The first is this stoichiometric CO2 footprint, which leads in part to the fact that ammonia has the largest CO2 footprint of any chemical that we manufacture today. In addition, these conditions are relatively harsh. So operating at greater than 700 degrees centigrade, 150 to 250 bar, these are conditions that are not conducive to distributed manufacturing. One has to operate at relatively large scales. These are plants that cost anywhere from $1 to $3 billion. And that means that we make ammonia at very large plants and distribute it out from there. And if that distribution is expensive, that can be problematic, as is the case today in many parts of the world. So we could perhaps overcome some of these challenges through a new paradigm, one in which we electrify chemical manufacturing. In this paradigm, we would begin with CO2 and nitrogen, and that could be sourced from air and exhaust gas. We'd start with water, and we would react these using renewable power at ambient conditions at 25 degrees C and 1 bar. These are mild conditions that in turn are conducive to distributed manufacturing. Furthermore, by operating at near ambient conditions, this enables the use of intermittent sources of renewable power, that a reactor can start and stop without having any thermal inertia or built-up pressure. We want to be able to convert these feedstocks, take the carbon atom from CO2, the nitrogen atoms from nitrogen, and hydrogens and oxygens from water, and combine those to make diverse products, to make fertilizers, paint, various fibers and fabrics. In essence, we want to make the material world beginning with just CO2, nitrogen, and water. So we can look at this in the case of ammonia. Imagine that we could take dinitrogen from air, take water, and convert that into ammonia and oxygen at 25 degrees centigrade and 1 bar using renewable power. We might do this in a way that is shown here. Take renewable power from solar panels, feed that to a local device, which can convert nitrogen from the air and locally available water to make ammonia, which can then be fed to a neighboring field, being used close to where it is produced. This kind of process could enable distributed production of ammonia. It could eliminate the carbon footprint here because we're using water as the hydrogen atom source instead of methane. So this could be a sustainable alternative. So we can look at this reaction in terms of its thermodynamics, the reaction of nitrogen and hydrogen going to ammonia. This is a thermochemical reaction, which is what we'll look at here first, one in which we are analyzing it based on its performance at various temperatures on the x-axis and pressure on the y-axis. Here we plotted the conversion x from 0 to 1. If the conversion is 0, that means we are fully at reactants. And if it is 1, that means we have fully gone to products. So regions which are blue are unfavorable from a thermodynamic perspective, while those which are red are thermodynamically desirable. So you may look at this plot and choose to start at room temperature, ambient pressure, where this plot is a deep red color, but that does not work because the kinetics are not favorable for this reaction. These molecules don't have enough thermal energy, even in the presence of a catalyst, in order to produce the product. So we're forced then to go to elevated temperatures, say 500 degrees centigrade. And at that condition, we have favorable kinetics, but the thermodynamics no longer work out, as you can see on this plot. One is in a deep blue region of this plot, where nitrogen and hydrogen remain as those reactants. We then apply pressure, going up to almost 250 bar. And at that pressure, one can achieve a single pass conversion of 15 to 20%. And that is how we make all the world's ammonia today. We can consider instead the use of voltage in the place of pressure. We start again, say at 500 degrees centigrade, applying a voltage instead to recover conversion. And we find that at 1/3 of a volt, we're in a deep blue region of this, in a deep red region of this plot. This is certainly favorable. And you'll see a clear qualitative difference between using pressure to drive conversion and voltage. That with pressure, one follows equilibrium contours, whereas with voltage, one cuts across equilibrium contours. With pressure, we're applying this driving force and staying in a similarly colored region. Whereas with voltage, we cut across and get to a region that is deep red. It also turns out that voltage improves the kinetics, so one could in fact operate at a lower temperature as well. So we can see here the clear advantages of using voltage for this reaction. Our lab has built a prototype that realizes these advantages. Here we are first splitting water using a water electrolyzer, making hydrogen gas, and feeding that hydrogen gas to a second electrochemical unit operation. This is the real innovation that we've made in our lab. A device that can take nitrogen and hydrogen and sustainably convert that into ammonia. This is done at 25 degrees centigrade in 1 bar, and this is a device that currently holds the world record for rates of producing ammonia at ambient conditions in a 1-pot process. This reaction is challenging in terms of its kinetics, and that's where our group has really had to innovate. And not just the kinetics, but the transport that gets species to these active catalysts. We've developed a lithium-mediated electrochemical cycle where first lithium and nitrogen react with each other to make lithium nitride. So this lithium is really doing a lot of the heavy lifting here by helping to break the nitrogen triple bond. This lithium nitride then undergoes a protolysis reaction. So it reacts with a proton donor in solution, and that proton donor allows us to make ammonia and make lithium ions. And those lithium ions are then plated in order to make lithium metal. All these processes occur continuously in our system. So if we look in, if we zoom in on the surface of the electrode, we'll find that lithium ions are moving to the surface, they're being plated. That lithium metal then reacts with dinitrogen to make lithium nitride. That lithium nitride reacts with the proton donor in solution, here ethanol, to make ammonia. And that all these things happen at the same time. So this is a relatively complex process that we're having to pull off at a single electrode. We can look at how our process that we've developed stacks up to other reports in the literature. So here in green, in red, in blue, and in purple, I've shared other reports from the broader community. And these are plotted in terms of their Faradaic efficiency on the x-axis and the production rate on the y-axis. You'll see that the system that we've developed, shown here with these black dots, is one which has a much higher production rate, 1 to 2 orders of magnitude higher than what has been shown before. In large part, what's important here is that we've broken the flooded transport limit in water and in THF. So that's the significant advance that our group has made. is in developing new reactor architectures which enable this high rate conversion of nitrogen gas to ammonia. The real difficulty here is that dinitrogen isn't very soluble in the reaction medium. And we have to find ways of contacting the gas phase nitrogen with a liquid phase non-aqueous electrolyte and the solid electrode where we are feeding in the electrons. And we've achieved that through a new metal mesh electrode, a new technology that we've developed that overcomes large historical challenges in contacting non-aqueous electrolytes with gas phase reactants. This is a technology that will be useful not just for ammonia synthesis, but also for other reactions that involve things like hydrogen oxidation, such that one can oxidize hydrogen at one electrode and then use those protons and electrons to hydrogenate organic substrates. So for instance, this could be used for pharmaceutical synthesis as well. So there are diverse applications in which this platform technology could find use. So we've talked so far about ammonia, and I want to emphasize in the very end here that this isn't just about ammonia, that this is also about making many other chemicals and materials that we rely upon. Our lab has made significant efforts towards the reduction of CO2 to CO. We've developed molecular catalysts which can conduct this reaction at extremely high rates. A lot of it enabled through control of kinetics and transport in this reaction. We're working not just on CO2 reduction, but on carboxylation reactions as well. So imagine if you could use CO2 to extend a carbon chain, to make a C2 into a C3 or a C3 into a C4. And if you could do that efficiently and sustainably, that's a new reaction that we've developed in our lab very recently as well. We're also working on epoxidation reactions. So this is part of a broader class of oxygen atom transfer reactions. Here at the anode of this device, we're splitting water, and we're taking these protons across the electrochemical cell to the cathode, the electrons through the external cell, through the external circuit, and those protons and electrons then react to the cathode to make hydrogen. At the anode, that O atom that's left behind then functionalizes an olefin to make the corresponding epoxide. So in essence, this is just a glorified water splitting device. We're breaking down water, we're making hydrogen, and placing that oxygen atom on an olefin instead of letting the oxygen atoms recombine and make O2, which we would just vent to the universe as a waste product anyway. So we're finding greater use for those O atoms. In addition, this process has a smaller thermodynamic energy input. Water splitting requires 1.2 volts, while this reaction shown here needs only 0.8 volts. So we can conceivably lower the energy footprint of water splitting as well. This isn't just about epoxidation, but about a much wider range of O atom transfers. Imagine if you could insert an oxygen atom into a CH bond and other related chemistries. So there are many possibilities here for sustainable chemical synthesis using water as an oxygen atom source. With that, I'd like to thank our students and postdocs who have worked tirelessly in this area, especially Nick Wazowski for our efforts on ammonia synthesis, which he helped to start in our lab, and then Joy Zheng, as well as Kyung-Suk Jin for the efforts they shared in the previous slide. And thank you very much for your time.